Well, I'm going to present you some experimental work, in a sense, trying to answer maybe the questions that many of us that are working with 3D printed materials or composite materials. Usually, as we saw previously, we do a lot of experimental work uh, to get mechanical properties, either to evaluate theoretical work, or if we go to more applied interest in the plastics industry, they are using typical experimental work for mechanical properties based on standards, HTM standards, and so on. So in a sense, when we do that, and we follow so well described experimental procedures by standard, in many times, we get, let's say, the overall mechanical response of the material. But when you have a highly or possibly highly anisotropic material that's coming out of a 3D printer, there is also a question is that maybe some of us who might have, what happens in situ? What happens inside? Are the properties uniform across the printed material? Or what we get, in a sense, is a mean value, an overall value, and what happens inside the material, the response of the material maybe is different. So actually, since we are working for many years with embedded sensors, I'm going to present that work, by bending sensors, how we can, the results that we got for out of mechanical testing by incorporating sensors in different plies as the specimens were printed. And also, I'm going, if I have time, since we are using the sensors, to present some results, how through the same experiment, maybe you can get some other answers related to residual strains, very characteristic for printed polymers materials, and maybe conducting some experimental work related on evaluating or finding the CTE, the coefficient of thermal expansion, or the of the material, or the TG. So by presenting some general information about additive and fused deposition modeling, I'm just stressing what I just said. We have parts that they are complex. They are there's greater interest of and we show some results out of 3D printed metal 3D printed materials, functional parts. What it comes out is that when we go to fused deposition modeling, and especially when we build composite materials by using this technique, and using materials like standard materials like ABS, PLA, nylon, polycarbonate, or PIC. In a sense, through that technique, we end up in a printed material that has anisotropy inside. So there is also, someone would say, either the process itself or the outcome of the process based on what kind of filament we're using, we get laminates or composite materials. So this anisotropy, in the inherent anisotropy of the material, how it is reflected to its properties, and especially the mechanical properties. So, and that dependence, we can also see that is associated to the chosen processing parameters, either how you print it on the printed board, either the direction, the orientation of the rasters, and so on and so forth, the printing speed. And there are many works out there trying to investigate the effect of the processing parameters on the mechanical properties. And of course, it's of great interest, especially when it comes down to applications for plastics industry using the advances of additive manufacturing on printing, either plain polymer based on polymer materials or enhanced composite polymer materials, since we get out many undesired defects. Either those are internals, are related to voids, to shrinkage, to strains, thermal gradients, venting, and so forth and so on. So the question is that, of course, we have a series of tests that we always follow to investigate those defects. So in a sense, what we try to do in that in-situ aspect is that we used fiber optic sensors along with temperature in order to present you some results about the temperature gradients, because also there is a question related to FDM is that how temperature gradients developed during the laminate building process, this sequential building process, layer by layer, how if the layers that they are on top of the printing board are affected by the thermal, the temperatures that they are exposed until the component or the specimen is built. So does that incorporates, brings in a difference in the mechanical response of the material in different layers across its thickness. So, as I said, we've been doing some work for many years now using fiber optics, since they present, many advantages. You can see some of them here. I'm not going to go through. In a sense, if we see it in a broader view, some I would say that incorporating such sensors, during the printing process, eventually probably we can talk about intelligent materials that can provide us information, not only during the printing process, but also when they are out there in operational mode. So, to make the long story short, let's come to the experimental work. So what we did is that we built testing specimens based on the ASTM D632 guidelines, type IV specimens. Our material was a nylon reinforced by 10% carbon, short fiber carbons, and you can see the parameters selected for the building of the specimens, and also in order to be able to handle some unexpected outcomes during the fabrication process. If you ever build such specimens out of that material, you can see that there is a tendency due to shrinkage developed during the processing process, and especially those flat ends, to curve. So the specimen was curving and coming out, was detaching from the building platform. So in a sense, we designed these Mickey Mouse ears layers, one layer, in order to make sure that it remained flat during the whole printing process. And what we did also, we designed some grooves only on the gripping tabs, not on the specimen. So this is, we had fiber optic sensors placed on the first, so that means one layer above the first one, in the middle of the specimen, so on top of the eighth, and also one layer before the last one layer built. And also at the same time, we incorporated the thermocouple in order to be able to have a simultaneously recording of the temperature gradients or the temperature developed during the building process. So and also one challenge behind that one in the incorporation of the FPGs goes to the alignment of the fibers inside the specimens. So in a sense, this was assured by not only by those groups, but also we had other devices that they were also either built simultaneously, or at some point we used simple magnets to keep them straight on the building platform. So by doing that, we incorporate them. Just to give you an idea, what we try to do is that to utilize the basic operating principles of the fiber optic of FPG sensors, which relies on the reflection of a specific wavelength when a broadband light travels through the fiber, and under axial strains, changing this spacing L that you can see here. So we get that response out of the refracted line and reflected light. And by using this Bragg condition, we can proceed to a general equation that includes that incorporates insight by getting by starting from the reference value. This is the one that is recorded after loading, and then we can have insight either the loading due to axial loading, external mechanical loading, either to thermal loading, and we can decouple it, or we can have all of them together at the same time. So this is the experimental setup. So you can see here, we have the specimen with the three FPGs on the first, in the mid plane, on the 16th layer, and also we attached externally an extensometer. So in a sense, we are measuring the strain due to mechanical loading simultaneously from an extensometer, as usually we do, and also in situ by using the three sensors incorporated, embedded in different layers across the specimen. So if we convert that to the stress strain curves, you can see here that despite maybe what we were expecting to see some significant differences, due especially for the mechanical response coming out from the fiber optic sensor that is closer to the bottom surface. That means earth layer. So that means that this layer is experiencing all the thermal gradients developed until the end of the building. We can see that the in situ mechanical response is pretty close, or actually I would say the opposite way. The one that we obtain from the extensometer is very close to the ones that were recorded from the fiber optic sensors. And also, since there's also a big question about when you incorporate such sensors, about the accuracy of the outcome, and that depends, of course, of how well the fiber optic is incorporated within the host material. Of course, if there is no good incorporation, the results are not reliable. You can see here a micrograph after fracture. You can see the optical fiber. You can see the layer that was laid on top. You can see the layer above. So actually, in a sense, after fracture, you can see here that we have a good adhesion between the fiber and the host material. And of course, you can see here that after fracture, there is a separation, a delamination, would say, between the adjacent layers. So in a sense, the results were very interesting, and actually, in a sense, it provides us that the general mechanical response of the material pretty much for that type of composite, where we have the short fibers along the applied load, the in situ mechanical response is pretty good and is very close to the one that we get out of an extensometer. So to go very quickly, those are some numbers that we get for the Young's modulus out of the extensometer and the fiber optic sensors. Of course, I would say that we did many times those experiments because we had many instances where the fiber optics were failing in very lows, in low loads. So just to give you an idea of the thermal response, you can see what's interesting here. You can see that during the whole printing process, the material is experiencing temperatures that they are quite above its TG. For this kind of material, the TG is close to 50-55 degrees Celsius. So we can see here that this is the whole printing process. This is from the middle and above. So that's why we brought it to the left. You can see that they have a similar thermal gradients developed during the process. But what's really interesting is that the material is printed way along its TG during the whole printing process. And going quickly, we use in different specimens, by using the fiber optics, we were able to measure the coefficient of thermal expansion, and also by using very close to the ones that we found in the literature, and also by using the same fiber optics in the tested specimens for mechanical testing, we're able also to calculate the fabrication residual stresses at the end, strains at the end of the fabrication process at different layers of buildings. So you can see that the values, we can say that the strains are of considerable magnitude, okay, but they are very close to each other, of course, with some differences as far as related to the ones in the bottom, the middle, and the top one. So these are the general conclusions. In the sense, I was personally expecting to see some significant differences between the first layer and the one close to the top. And it was really interesting to get the outcome that doing a classical testing by using an accessometer, we can get the mechanical response that it seems that is the one that of the material in different layers. So, of course, this was placed in the framework of a work, of an industrial work. And before I thank you for your attention, please allow me to let you know that in a year from now, from September 6 to 11, the Greek Society of Experimental Mechanics and Materials is hosting and organizing the European Conference on Fracture in Athens, Greece. Is going to take place in the center of the city, and same as here, we plan to have a summer school, different many parallel technical sessions. Of course, we're going to have plenary sessions. We'll have special focus symposia, poster sessions, and of course, I will invite some industrial partners to take part. So these are the fees. I think that the registration is open since yesterday, September 15th. If you are interested, get into the internet and find the related material. And we hope we'll see you in Athens, Greece in a year. Thank you very much.